Good morning. Can we start the
Good
program?
morning, sir.
Morning. Okay.
Yes,
So I
sir.
welcome all of you for the second session, second day of this capacity development program on health diagnosis of rotating machinery. Today we have a chief guest for this program, Dr.R.Prakash from National Institute of Technology at Trichy. He is currently working as an assistant professor in the Department of Mechanical Engineering, MIT Trichy, Tamil Nadu. He has completed his two postdoctorates from Texas A&M University and Qatar in 2018 and 2019 respectively. He received his PhD degree in Applied Mechanics from Indian Institute of Technology, Madras, Chennai in 2015. His master degree in engineering design from College of Engineering, Gindu, Anna University, Chennai in 2010. The bachelor degree is mechanical engineering from Erode Engineering College, affiliated to Anna University during the year 2005. He has 7 years of research experience and 3 years of teaching experience. His current research interests include mechanics of composite structures, condition monitoring of rotating machines, computational mechanics, mechanical vibration, and structural health monitoring. He has published in several reputed journals such as Journal of Sound Vibration, Composite Structure, Sensor and Actuator, A, Physical, ACTA, Mechanica, Train, Structural Engineering and the Mechanics, and also published a book chapter in Springer. He has presented his research work in various international conferences across the world like USA, South Korea, Qatar. He has collaborated in various projects with renowned professors in the field of structural machines, mainly Professor J.N. Reddy and Professor Emeritus C. Logodo from Texas A&M University, USA. Professor Sami E.L. Borgi from TAMUQ, Professor Michael Criswell from Varnasa University, UK. Now I welcome you, sir. Now I will hand over the session to Dr. R. Prakash. Over to Prakash, sir.
Thank you, sir. Thank you for your introduction and thank you for your invitation for this program. Okay, yeah. So let me start. So my screen is visible now. My screen is visible, or all of you can see this?
Yes, visible, sir, visible.
Oh, fine. Okay.
You maximize the window, sir.
Yeah. So, good morning to all. I'm going to talk about the condition monitoring of turbine blades using vibration techniques. So, this is the work which I have done during my postdoc with my collaborators at Texas A&M University at Qatar, as well as my collaborator with Swansea University. Okay. So these are the overview of this today's talk. Start from the failures in gas turbine blades and what is the objective of this study, and then we start with the numerical modeling. And here this is I'm going to introduce a new concept called the variable packet transform. So this is like the hierarchy of the variable transform. How this, the transformation technique is essential for the identification of damage in the turbine blades. And we have done some numerical analysis as well as the experimental analysis, and then we correlated both, and finally we arrived at a summary. Let us see the failures in gas turbine blades. Normally, the gas turbine blades are predominantly used in oil and gas industries, in power plant engineering, and even the aircraft. So, it is very essential that we need to monitor the turbine blades during the operation. So it is very challenging also. It is very difficult to monitor the condition monitoring of, or you can say the blade condition on during the operation stage. Since it rotates with a very high speed, and still it's challenging and task to monitor such a situation to monitor the gas turbine blades. So if you see the previous studies have reported that around 42% of gas turbine failure occurs due to faults in blades. Okay, due to like a very small amount of, because it's rotates high speed and also experiences a lot of the steam or gases, whatever that. So impinging on the blade, so it's subject to get mechanical load, the fatigue load, and due to that the blade may get cracked. So it has even the small amount of crack if you are unnoticed, and it leads to be catastrophic failure. So that is the major failure. You can see this is the catastrophic failure. It's a case study. You can see the pictures. This is the catastrophic failure of 171 megawatt of gas turbine, leading to more than 25 million USD due to the downtime production. Okay, that means due to this the downtime production so financially loss incurred. So because in the oil and gas industry, the turbine has to run for 24/7. You can even stop for some 1 hour, 2 days. A huge loss for the oil and gas industries. So it is very, very essential that we need to monitor the gas turbine blades during its process. So one of the most encountered problem in gas turbine is the blade mistuning. What is meant by blade mistuning? Let us see that. So the blade mistuning is nothing but if one of blade, the properties of one of blade slightly varies. Okay, due to the geometrical or mechanical property, because when you manufacturing the blade and we have to provide the more accuracy, and even then we cannot make the blade identical. So if you have, let's say, you have some 100 blades are there in a single state, in a single stage.
Excuse me, sir.
Yeah.
Sir, your voice is echoing, sir.
Because of this ambience, actually, I'm in a room it's nothing is there. That's why it's. Right. Let me. I'll just remove the audio. Okay. I'll just speak without the headphones. Is it okay now? Am I audible now?
Yes, sir. Yes, sir.
Okay. So, if you see, this is we cannot make the identical blades, right? So, even then, if you have used the precise manufacturing methods, it's still difficult to manufacture the identical blades. And therefore, what will happen due to the changes in the mechanical or the geometric properties that exist in the blade, so which leads to some kind of defect. Like it says it gives some slightly or a small amount of changes in the property. It gives the response. The response increases substantially. So that's called the mistuning. That means if the properties are one or more blades vary slightly, so then the response can increase substantially. So that is due to this. So the manufacturing tolerance or the variation in material or geometrical properties. Okay. And also the damage to blades causes mistuning. So that has received the limited attention. So the damage also considered as a mistuning. Okay, any small amount of crack, and which also can increase the response substantially. Okay, so that is also a mistuning. So in our study, what we have done, we have intentionally made some mistuning, or let us say we make some small amount of adding some mass and causes the mistuning effects. So, our study is to how to identify even a small amount of crack in a rotating, in the blade at disk as well as the rotating, blade conditions. That means when the machine is in rotating conditions, how we can monitor. So we have used several methods that we will discuss. So the objective of the work actually to detect presence, location, severity of the damage or mistuning. As I said that damage also causes the mistuning. So the damage and mistuning here I will be saying that both are same. Okay. In bladed disk and the rotating blades of turbo machinery using the Wheel packet transform algorithm. Here I am going to use this word. This is a very this is the advanced signal processing algorithm, which is currently people are working in this area. Like there are different advanced processing signal processing algorithm. So that we will discuss. This is the main algorithm which I used to detect the damage in the turbine blades. Let us see this. I am going to talk about the numerical simulation. Initially, I have
Your slides are not changing, sir. Your slides are not changing. We are only able to see only the first slide.
Is it so?
Sir, slide is not changed.
Now it's, well, let me go exit out and then I will come back.
Okay.
Because for me it's like I'm going. For me, it's, I didn't see anything like that's no difference. Let me share again. Am I audible?
Yes, sir.
Is it okay?
Yes.
One second. You can see the changes in the screen now.
Yeah, we can get the second slide, sir. We can see the second slide now.
Now the failures in cache redundancy is.
No, sir. No, sir.
Okay. Sorry, actually, for me, it's there is no difference. As if I'm. Okay. So can you see this now? This blade? Okay. So I have already mentioned. I just quickly go through this. What is failures? So you have seen this is the failure of turbine blades. So you have already studies are reported 42% of gas turbine failures occur due to the faults in blades. So in that, one of the most encountered problems in gas turbines is called mistuning. So the mistuning is nothing but the properties of. Now you can see this changing.
No, sir, still not changing.
Still screen is not changing, sir. There in the second slide only.
Okay. Now it's fine. Okay. Let me. I don't want to make this in the presentable screen, like in the full screen. Maybe that is the problem. Now we can see, sir.
Yes, we can see, sir. But once you are changing, it is not changing.
Yeah. That is the problem here. I don't know the technical reason here. But so okay, I will minimize this. Now we can maximize this one. Is it okay now?
Okay, sir, but the slide is always keeping one slide, sir. You are for changing, it is not observed in the monitor.
Actually, I'm changing now, but
now it is changing, sir. You can do
now it is
the
changing.
Yeah.
Is it changing now?
Now it is changing.
Okay. Just let me know if because I'm going to other slide. Yeah. Okay. Because I don't want to make it in the full screen now. I think the problem with the full screen. If I make the full screen, I don't know why it is not showing that one. So yes. Okay. So the blade mistuning, if you see that the property of one or more blades varies slightly, then the response can increase substantially. So that is due to this happened due to the manufacturing tolerance or variation material geometrical properties. I said that, and the damage also caused mistuning. So which receives the limited attention. So that's what we focus in this study. Identification of mistuning, the blade is as well as the rotating blade. Can you see this now? Objective of this. Next slide. Excuse me, sir.
Yes, sir, we are able to see it.
Okay. Yeah, please. Because when you see something like if you don't see anything, then just let me know. Because I feel that I'm moving on. Like. Okay. So the objective of this work is to.
Your voice is breaking. One of your video.
Okay, let me try to use, because if I use a headphone, then it will be better. Am I audible now? Hello?
Yes, sir.
Okay.
Yes, sir.
Because, okay. So the objective of the work is to detect the presence, location, severity of the damage in bladed disc and the rotating blades of turbo machinery using this Weber packet transform algorithm. So I will discuss this Weber packet transform in the upcoming slides. So I will go one by one. So let us. So initially we started with the numerical model. So the numerical model, let us say the turbine blade. The numerical simulation. So basically the turbine blade in a single stage. If you see there is a n number of blades will be there. Let us say we have n number of blades, and in order to model that, so we actually use the spin mass system in order to model the blade as well as the disc. Okay. We consider the 2 degree of freedom model. This is the one sector. Okay. If you see, this is the one sector, and which consists of disc as well as the blade. So each considers a single degree of freedom model. So we have for blade 1 degree of freedom model and another degree of freedom model. So which predicts the exact timings of the rotating machines. And we connected the neighbor sector using the laser wire, and this will be like this sector, connecting all the blades, and so that it will cover 360 degree. Okay, so entire blades of the single stage rotor. So this is the we have used this spring mass system, and in the vibration we have studied that the spring mass system. So we use that one, and also we consider the damping, that's the proportional damping method. And we assume that each blade in assembly has one significant mode, that is the first bending mode. And in this study, we have not considered any centrifugal stiffening or the rotational dynamics effects are considered explicitly in this model. So this is the simplest model, and which probably gives the time response of the individual blades. So once we get the time response, and then we will use it for the damage identification purpose. So that is our objective. And here we use this 20 blades for the simulation, and one of the blades we use to mistune. That means it's nothing but we use the damage by reducing the stiffness of the blade. Normally, reduction in the stiffness, which causes it's called as a damage. Okay, any changes in the stiffness. So the modeling of dynamics of the bladed disc, this is a typical equation of the free vibration. Okay, and this is the mass. This is the mass matrix, and which which accounts both the mass of the blade as well as the disc. This is a 2 degree of freedom. And similarly, we have the 20 masses, like sectors will be there, like 20 blades. So we have the 20 sectors. So we have this because each sector has 2 degree of freedom. So therefore, we have the 20 blades. So totally 40 degree of freedom will be there for this entire turbine blades. Okay, for the single stage roll. And this is the M is a mass matrix, C is the damping matrix, and K is the stiffness matrix. And if you see, this is the Q of T. This is the vector of displacement which corresponds to this 2 cross 20. That is the degree of freedom. So totally 40 degree of freedoms are there. Okay, and therefore this is for vector which has the 40 cross 1 dimensions. And this is the stiffness matrix. This is a coupled stiffness matrix which accounts this. Both this lazy wires also accounted. And if you see this one, and if you take this individual stiffness matrix of the blade, and you can see the Ka is the stiffness of the blade, and this is the coupling effect, and this is the we consider this when you connect it with the disc, and this term will be there, like Ka plus Kd plus 2 into Kc. That is this 2 times of. If you take one, this the 2 lazy wires will be connected, and then the disc, and then as well as the stiffness of the blade. So which account this stiffness matrix will be taken under all the physics of the problem. And here you can see this is the Ka. This is the stiffness of the lazy wire, and so this is also we have for the coupling of that, because we are connecting this entire like physically connecting, but we have to mathematically we have to couple with this matrix, so that we will get that combined effect of that. And we use the proportional damping matrix, which is the random method. So the alpha and beta is a coefficient, so proportionality factors which can be obtained from the experiments. Okay, and from the first 2 modes. Okay, after that we can use it for this damping. And here the damping ratio for all modes we consider only 1%. And in this mistuning, the mistuning is just, I said that we're just reducing or altering the stiffness of the blade, and you can say the reducing the stiffness of the blade is called as a mistuning. So we can reduce this as a percentage of the delta B is a percentage of reduction, stiffness reduction in the mistuning. So whatever percentage we will reduce, that is which that much amount of damage that causes to the blade. So that happens to the blade. If you see this from this model, we got the response. If you see this alone, can you see this full screen now? Yeah. If you see, this is the displacement or response. This is a time response. So displacement versus time, and the blue color, that means which indicates that the tuned blade response. That means tuned means without any damage. So the blade is without altering the stiffness, as if that is the manufacturing, like it's a original configuration. And after we obtain, like if you see, this is the response of that. Actually, here you see that we have just for the graphical representation, we just want to show only the few blades. Though we get the response of 20 blades, but we get just only the few blades for the understanding. Okay. And here one of the blades got damaged. And that means we just induce a small amount of damage in the blade, that is the blade number 3, and this is the neighboring blades, the blade number 2 and blade number 4. And if you see the response, from the response you can see there is a small for neighboring blades, like tuned and mistuned response almost similar. And also if you see compared to this one, because this is entirely like the mistuned one, only the blade number 3 where just give some small amount of damage. And when we compare this 3, and we notice it's very subtle, and this small changes are even, it is unnoticeable, this changes. And very difficult to identify the damage in even the numerical condition. Even in the experimental case, we have a lot of noise in there, and we have to, given in that condition, it's very difficult to extract the damage information. So that is the reason in the time domain. So the time domain is very difficult. So what happened? We convert into the the frequency domain. So there is a transformation that happens which converts from one domain to time domain to the frequency domain. Why? Because whenever there is a signal which is in the time domain, it's very difficult to extract the useful information. When we convert into the frequency domain, so we will get the useful information with a small amount of data. Okay. So therefore, we use this like frequency domain. So this is called the frequency response function. Most of you in the, if you are on vibration, you would have noticed that the frequency response function simply called as a FRF. And so here you can see this is that displacement versus force. Like we give some kind of impulse force. So we actually numerically add some impulse force. Okay, I will explain that how we do it in that experimentally. But in numerically, we just apply the impulse force on this one blade, and we will extract the response, the displacement response of all the blades. And if you see that there is a frequency response of the blade as well as the disc. So if you see, this is it's around 12 hertz. If you, it just coincides with the x-axis, and similarly the second peak, this is correspond to the disc frequency. So, and this is for the blue one is corresponding to the tune, and the red one is the corresponding to mistune. So there is no difference. If there is small, any changes in the damage, or if you use the damage, there will be small amount of frequency shift. But even then, it is not noticeable in this, the theoretical frequency response function. Okay. So therefore, it is very clear that it's a small amount of damage is not visible in the frequency. That means in the Fourier transform. This is a kind of a Fourier transform. So most of you know that in engineering we have already studied that Fourier transform. There are different type of transformation and techniques are there. So like Laplace transform, and similarly we use the Schottky Fourier transform, like and then Weber transform and the Dimble transform. There are many other transform techniques which converts a signal from one domain to the other domain. Okay. So I just moved, sir. Can you see this now? Can you see the changes in the slide now? I just moved to the next slide.
No, sir. No, sir. We have not.
No.
Only with the time domain signal is there.
Okay.
Okay, sir.
Previously you see, right, this one. Previously you see this, right?
Yes, sir. Yes.
Okay. So now this is the mathematical. So why we need to transform? Okay, that signal. So normally the signal that you obtain from the experiment is a time domain signal. So most of you have done that experiments, and vibration signals are the time domain. As I showed that is the free response, the free vibration response, and that is in the time domain. So it is very difficult to extract information from the time domain. Therefore, we need to transform that signal into the other domain so that we can extract the information from the signal. Okay, so there are such transformations. So most popular transformation techniques called the Fourier transform. The Fourier transform, it's nothing like if you see this is the Fourier transform that we have already shown that the FR, and we'll see that what is the Fourier analysis, and then we'll go to the Fourier transform. The Fourier analysis, like we have already studied, it's a frequency component. Okay, let us say there is a signal. Let us say there is a signal like you can see this is there's a sinusoidal signal, it's a decaying curve, and so any signal which can be like made like this. So any signal like this, and we can write it like this. So you can decompose into many signals. So signal can be written like this, and then so if you add this to all this, sum up all this, and then you finally will get this. So basically, any signal you can decompose into sinusoidal curve. Okay, that is why if you go to this the basis function, of the Fourier transform, and this is the complex exponential. So this consists of the sine plus cosine. Okay. So any any signal we can write it in terms of sine signal. Even the cosine signal we can write it with the sine signal with including the phase, which includes the phase. Okay, so the sine signal is a base signal for any type of signal. Okay, and so that's what we used in the Fourier transform. So Fourier transform we use the complex exponential which consists of the sine plus cosine signal. Okay, and even the cosine signal you can write in terms of sine signal. And this is the frequency and this is the time domain signal. So whatever experiment results that you are obtaining or the numerical results, that is this one, x of t, which converting that into the integration of the limits. We use the limits, but here we just generally I mentioned, but generally use 0 to t, the time 0 to t, and x of t, and this is the component, I mean exponential component, and this minus is the decaying one, and this is the dt. So when you integrate over time and get the response of the mean, like you get the response in the frequency domain. Inverse, if you take the inverse Fourier transform, then you again get the, you will reconstruct the signal again. That means again you will recover the original signal. So that is the beauty of the Fourier transform. Okay, and if you see, there is a one problem in that Fourier transform that, or we can say it can handle only the periodic signal. Okay, so most of you understand what is mean periodic and then aperiodic, and the signal which repeats equal interval of time is called a periodic signal. So if the signal doesn't repeat, I mean, or you can say that particular feature is not repeating equal interval of time, is called a periodic signal. Okay, the simplest periodic signal in comparison, the harmonic, and that's what we discussed in the entire vibration in the analysis. And also there are different type of signals are there. Okay, even the random signals are there, and here you can see this is the, if you convert this from what time domain to frequency domain, what will happen? So we convert it to frequency, but the missing part is that we have only the stationary part. That means if the signal changes with respect to time, then we can notice from this Fourier transform. So when that particular signal or where the particular signal that happened, so that information is missing, that we cannot compute from the Fourier transform. So that is the only drawback of this method, and so this is the Fourier transform again, converting this x of in terms of omega signal. Okay. So like I said, this is a signal, and which convert into from this is a complex signal which convert which we can decompose. The Fourier transform basically what it does. Actually, it decomposes into many sinusoidal signals at different frequencies. So such frequencies are low frequency and low frequency to high frequency. So it's going from low frequency to high frequency. And so this is what we have actually we get from the single peak. This is the one peak like another peak like another peak. So we get but this can be computed only for a stationary signal. The stationary signal means the signal properties, that means the statistical properties of the signal does not change over the time in the stationary signal. In non-stationary signal, it changes with respect to time. Okay, for example, the chirp signal, and the chirp signal which always changes with respect to time. Okay, so that cannot be analyzed through Fourier transform. Okay. So that's what we will see that one. What is the stationarity of the signal? Okay, the signal with the frequency content unchanged with the time. Okay, so signal frequency content. Okay, and then I said the statistical property, average, standard deviation, variations, and all variations will not change with respect to time. That's called a stationary signal. It's the simplest. We normally assume, right, in the mechanical problem, linear, elastic, like that in signal processing, they assume that stationary signal. And the non-stationary signal is nothing but the frequency changes in time. For example, chirp signal. And if you see this is the stationary signal, I will give you some example of that. What is this? We have that. Let us say if you get any signal which will not be which consists of many frequencies, right? So let us say any structure, if you find out that what is the use that model analysis, you can get some you will get the many frequencies like that. So we get some many frequencies like the 2, 10, and 20. Okay, and you see this is the curve. And when you convert it into the Fourier transform, we get the Fourier frequency component like 2, 10, and 20. So you get the spikes at the exactly the same frequencies 2, 10, and 20. But this signal doesn't vary with respect to time, because if you see this, if you notice this keep continuing, and this frequency content it will be constant over the time, okay, entire time period. And if you see, whereas if you see the non-stationary signal and zero, the same signal, frequency component, and but for the different timing, 0 to 0.4 second, and 0.4 to 0.7 second, 0.7 to 1 second. So the frequency keep on changing, 2 to 10, 10 to 20. So it's starting with 2, and then it's going to 10, and then 20. So it's like a 20 is here high frequency, and then low frequency, and minimum and low. And if you take this signal and just convert into Fourier transform, take the Fourier transform to find the signal, frequency signal, and see this is the, like, we can see this is the 2 and 10 and 20, but missing part is where particular changes happen. It should show exactly at the 0.4, but there is no position of in this domain, because it is only the 2D graph. Okay. So it's a 2D graph, so it's very difficult to see the third dimension. So the third dimension is very important, when and where that particular signal component that changes. So that is missing of the from the Fourier transform. So that's a drawback of this method. So that's what the Fourier transform gives only the what frequency content or component exists in the signal. Okay. And time and frequency cannot be seen at the same time. So we have seen only the frequency domain. So we see only the frequency, so which converts the time from the time to frequency. So both the time and frequency cannot see at the same time. That is the drawback of that. So therefore, time frequency representation of the signal is very, very important. And that is the one earlier solution is called short time Fourier transform. The short time Fourier transform, which we proposed much earlier. Okay, so and that was the method which gives both the time and frequency information. And so the Dennis Garber in 1946 he used STM. This is much earlier, and what he used actually use this the time frequency. So if you see, this is a three-dimensional plot actually. If you do the x and y axis, there is another axis called the z axis, which is the magnitude. So if you see, this is the 3D graph. We have the z axis, which is normal to the xy plane. So and if you see, this is the bricks of uniform size. That is the window actually. So. And if you see the function, this is the same basis function, but there is some window. There is another weighting function. This is that's called the windowing function. That is the which used for the take the windowing function, and it's a kind of template. So it's a template which used only one single template we have. That is the one the sign again, the complex exponential, and signal is segment of signal is assumed. Not stationary. That means not normally what we have done in linear or non-linear problems. We actually what we do, small amount of portion we take and consider as linear, and then similarly we take the very linear part and then we construct it, and then to see the non-linear to find that using the numerical method. Similarly, in this method, we most of the signal, even the non-stationary signal, we consider the small amount of portions as stationary, and we use the segment. The segment of signal is assumed stationary, and this is the constant window. So this window start from the origin of the signal to till the end of the signal. So it is just matching and then computing the correlation factors. So the correlation coefficients, and this correlation coefficient which reflect over here. Any changes are, you can say that if it is fully correlated, it gives high correlation. If it is not correlated, it is template and it gives a low correlation factor. So this will give this where some any changes that happens. So it's completely from the correlation factor we understand there will be some changes that happen as well as the frequency as well as the time. So when the frequency happen, and particularly where when and what frequency happen. So that information we can extract from this signal. The problem even in this method, we use only the constant window technique. This is a constant window. The resolution is not is constant. The resolution cannot be adjusted. That is the drawback of this this method, and the drawbacks of this method. The unchanged window constant window, and there is a problem here that this is a narrow window. So if you see this the left hand side figure, and this is a poor frequency resolution. If you see this the curve like this, the bell curve, and there is it's a wide width actually. So that gives a poor resolution, frequency resolution. But if you see this, the time resolution will be good. And similarly here and the right side the wide window, like wide window in the time domain, and here the frequency resolution will be good. So what happens? This can be achieved only this based on this the Heisenberg uncertainty principle. In that actually, one cannot find that both time and the frequency both cannot get both in the good resolution. One has to compromise either one side. Okay. If you want the frequency at one particular point, you can capture that with good accuracy, and we have to compromise that time. Okay. So one cannot achieve both. That is what Heisenberg uncertainty principle says. So in avoid this drawback of this STFP, there is another method called the Bayesian transform. This is the alternative approach to the short-term Fourier transform, which overcomes the resolution problem. Okay. So what the Bayesian transform? So the Bayesian is nothing but like you see here. Okay. So this is kind of adjustable window. Here we use this constant window. It's like a zooming lens. So we use the zooming lens, right? So for the magnification factors, like for the higher amplification factors, we use a different zooming lens, right? Similarly, we use a different zooming lens for a different magnification factor. Suppose you want the high magnification factor, we use this high resolution zoom, right? So and such way we use a different type of functions, okay, and different type of functions, and kind of it's a zooming lens only. So zooming windowing function. So which can see that any small amount of changes in the signal at particular point or where that location happens, you can use this lens to find out that. So in here this good time resolution and poor resolution, poor frequency resolution at high frequency. In that high frequency, we will get a good time resolution and poor frequency resolution at high frequency. Whereas in the good frequency resolution and poor time resolution at low frequency, we will apply. Okay, so here we can let us see here. This is the wavelet. Actually, anything you can call it as a wavelet which satisfies a certain conditions. Then you can call it as a wavelet. So we ourselves can make our own wavelets, and that wavelet is a short time, very short signal which added is zero. Okay, and the wavelet is a kind of waveform which is a limited duration that has an average value of 0. This is sine wave is a basic wavelet function. So wavelet function. It's a kind of wavelet function, and there are different wavelet functions. Diversities, Haar wavelet, Gaussian wavelet, and there are many number of wavelets are there. So if you are interested in this field, you can work on that. There are any number of different type of wavelets are there. So this is the kind of, so each wavelet has its own properties, and we can use it for the different application purpose. For example, we can even use it for the face recognition techniques, or image compression, or even noise reduction. There are n number of applications are there for the wavelet analysis. So the wavelet analysis, we just use this application of wavelet analysis for the data generation problem. In general, wavelet analysis has n number of application. This is a mathematical technique. Okay. So which has the properties of that the short time localized wave is zero integral value and possibility of time shifting. So we can shift it time for flexibility which convert from the time domain to the frequency to time domain. So that is a frequency. So how we can this is the basic equation of that the continuous wavelet function, and this is where B is the shift coefficient and A is the scale coefficient. This is nothing but the frequency as well as this is a shifting parameter. Okay, and like we have seen in the Fourier transform, the x of t, and there you have seen that E minus the 2 pi of t, right? So there is a complex exponential function. There is a one function, but here the wavelet, mother wavelet. So mother wavelet can be anything. There are many wavelet functions. It's not only one wavelet function. unlike the Fourier transform, there are many wavelet functions are there. Like I said, the Debouches, Gaussian, R wavelet, Shannon wavelet. There are many wavelet functions are there. For different application, we use it. And the T is a time, and B is a shifting parameter. The shifting coefficient, A is a scaling parameter. That's a coefficient. This is the scaling is nothing but inversely proportional to the frequency. Okay. And this is the 1 by root of A is a normalized value. So because energy computed in time domain and the frequency domain should be equal. So that is the property of that wavelet function. So how do we do this wavelet transform? Let us see that we actually take a time domain signal and take a wavelet and compare. It's like I said, that's a template. This was a template with our we can make our own resolutions. So the resolution in the sense we can just we can take this one, the initial mother wavelet. You can take this mother wavelet and you can compress it, expand it, and then you can shift it. Okay. So that is the flexibility of this. And take the wavelet and compare with each section. So the each section, how we compare, like. So you take the signal and small, this is a wavelet function, and which you compare the small signal segment, and then you will compute that how closely the correlated the wavelet is with the signal. Okay, and this higher this C is the more the similarity, so which gives some number. Okay, so this is kind of call it as a correlation factors. So and we can just move on to the different segment until end the entire segment of the signal. Okay. And if you see this one, the whole signal will be covered like this. So the wavelet will keep on moving. This is some B, it's a translation, and then scale. And next is scaling. That means you are increasing the stretching the scale. That means you are just stretching the wavelet function. Now again you do the same operation and repeats the operation from 1 to 3. Okay. So the steps 1 to 3, and again finding the correlation factor. After this, finally once you complete the signal, entire signal, so you will get the like this. Okay. So you get the time and scale. This is the frequency. There is an inversely proportional to the frequency. Scale is inversely proportional to the frequency, and z-axis is the coefficients. That is that's why you can see that particularly one x-axis, and then particularly here that inversely proportional. That means the lower the scale is higher the frequency. The higher frequency you can see the small changes, and here also you see the changes. There is a peak indicates there is some changes. So in the signal. The damage detection purpose, how we can take the signal and we can see this is how the signal changes. How this particularly this time signal at a different location. Instead of time, we use it here. Instead of time, we use the space. We can either time, we can use the space. And what we can do for the damage detection application, if you take any beam or use this measurements for one location, location 1, 2, 3, 4 like that until n location. Okay, until n location. And we take the measurements and then we can send it this signal into the wavelet transforms, and this will compute this coefficients, how this the coefficients like compare with the wavelet functions, and then we can see that one. So we will send both the damaged and undamaged signal, and then any changes in the signal which gives this spike like this, so which indicates the damage location. So instead of time, you can use a space for that, to identify the location of the damage. And this is the resolution of time frequency. I said that here you can see this. Earlier you can see the lower frequency, you get a better frequency resolution, and the poor time resolution. As you go higher, like here you select, you get the poor time resolution. Here you get a better time resolution, poor frequency resolution, because frequency is the y-axis. So it's a band, very high bandwidth. So it's very poor resolution in that. So earlier you can see the low frequency get high frequency resolution. Okay. So this is the resolution. This is a comparison of different transformations. So when you time series, so this is the time series signals. The signal doesn't change constant, and we will see this is the time frequency, like the time, and only the frequency component you can get it. And here the only the time component or time information only we get it. Here the only frequency information. But here the short-term period, both information will get it. At any point x and y, you can get the coordinates, and you can get the time as well as the frequency information both. And this is the wavelet transform where you can get the adjustable time. So this window is the constant window, but here this is the adjustable window. Wherever you want that frequency change, resolution you can increase it. So this is kind of adjustable window technique. And let us see that how this continuous wavelet transform, and there is a problem with I said this is a continuous wavelet means the signal is not at all continuous, still it's a discrete signal that only you are taking. And so there is a problem in the continuous wavelet transform. This is highly redundant and it is difficult to use in the practical in the implement for this damage limitation cases sometimes, and it increases the computation cost. So you have enormous data that required for this work, which is difficult to get from the experiment sometimes, and therefore we move into the discrete wavelet transforms, which is nothing but just discretizing this discretization of the wavelet transforms, which is saying that A of like instead of 1 by root 2, there is here that is the 2 of j, power of j by 2. That is a j is nothing but this scaling 1. Okay. And T is a time, and then T is a translation parameter, and this sign is the wavelet function. Okay, and K, J and K is the scaling function, that is which indicates a frequency. You can say the scaling function, that means the decomposition and so the level of decompositions. So let us see, this is the signal. Okay, we can compute like this. Any signal, time signal, which can, or we can say that, and which can be decomposed into different type of signal, like discretized into two components, like the low frequency and high frequency components. So low frequency is called approximate coefficient, and decay is the decay coefficients, the high frequency. And there are different levels. If as the level increases, your bandwidth is increased. Let us say you have the frequency of 0 to 100 Hz, 0 to 100 Hz, and the frequency of the structure or any value, any structure, it's a 0 to 100 Hz initially. So this will compute 0 to 50 and remaining, and this will take the 50 to again 100. Okay, that means exactly that start with that one. So it takes a high frequency component like that. So here this is 0 to 25 and then 0 to 50. So this part again discretize that, again the low frequency component of this. So likewise, we can get this 0 to 12.5, and here this is 12.5 to 25. Yes. So likewise, discretization happens. So it's left that the high frequency component. This is the data. So further, it will not decompose this the detailed coefficients. Therefore, you see this is the coefficients of this one, and this is the, if you just sum up these signals and then you finally get the original signal. So this is a problem with since this is not decomposing this, and there is a redundant, and there will be some missing, that because the damage that occurs in the high frequency components sometimes is missing in that, because it's not extracting or decomposing the detailed parts. Therefore, the wavelet transform, packet transform, earlier I said that the wavelet packet transform, this is what I used in my study, the wavelet packet transform, which is a kind of extension version of that that means DWT is a discretized wavelet transform, which completely decomposes. Previously, the one which is not decomposing this D1, that means the detailed coefficient, but here this is completely decomposing. It's a complete binary tree, and you can see this is a signal which computes all the taking this 100, let us say, and then this is decomposing like this 0 to 50 and 50 to 100. So likewise, you can start with this 0 to 25 and 25 to 50, and this will be like 50 to 100, sorry, 50 to 75 and 75 to 100. So further, if you decompose this signal and increase the level of decomposition, and further you fine tune the bandwidth. So the higher the level of decomposition, lower the bandwidth. So you can easily fine tune, or you can locate the particular damage that are falling in that frequency bandwidth. So that is the objective of the study. And therefore, this is the mathematical equation, and this is the kind of the original signal. When you sum up all the individual decomposed signal, and you can get the original signal. And finally, we can obtain this each here this f of t is a decomposed signal, the time signal, and this can be written like this: the coefficient. I mean, C of I j k. The I is this is I is like nothing but this the modulation parameter. So this is a frequency modulation. This is nothing but this one, and so I j k is in modulation, scale, and translation parameter. So this is a frequency component only. For this, I mean, in addition to the previous equation. And finally, what we can get that we get actually the time series of the detailed coefficient. So that means the decomposed component, and which is nothing but this is the isolated correlation factor. So this is the correlation factor, and this is the value function. Okay. And due to the orthogonal property, we just take this one, and we can compute this approximate and detailed coefficient for the different signals and lower frequency and high frequency. So for both we compute like this, and we understood that sometimes the very small amount of damage that occurs in the in the detailed coefficients. And what happened? We just take that particular signal bandwidth. That means only you take this, consider only the particular bandwidth, and you take this time that time series of the decomposed signal and take the square and integrate it. That's called energy of the signal. So this is called a wavelet packet energy at particular I component. That means that particular frequency bandwidth. And this bandwidth, this energy which gives this that damage information then we can compute for the damaged signal as well as the undamaged signal. So you take this difference and then the modulus of that with respect to that undamaged case, and this will give the energy change, the rate of energy change. That is the change in the signal wavelet packet energy. Okay, and this will give the good indication of the damage. So this is the algorithm we used for that. Initially we take the time response and then we signal process it and choose the level of decomposition using the entropy method. This is the kind of method which you optimize the level of entropy, different level of decomposition. So we obtain the optimal level of decomposition, and this is the threshold value, which is a statistical value parameter, and that's called using the upward confidence limit. So we use this statistical properties of that one, and we can use this threshold value. Any value which exceeds the threshold, then we can call this the damage. Let us see the results of that, and finally we find that the location. So once you find this, as I showed the time response, we cannot find anything. But once we use this wavelet packet transform, and we use the damage index called the Trichy, and when this subtracted with this threshold value, any value you see, this is the damage at a particular 0.5%. I guess just give a very small amount of damage called 0.5% of damage at blade number 3 and different there, and you can see this a total number of 20 blades, and you can see the high the sharp spike which indicates the damage. We can easily locate the damage, which blade the blade has the damage. So, and this is the neighboring blades which has the coupling effect. Due to this coupling effect, so this small this changes because of this effect of the blade, damage blade. So which affects the neighboring blades also, and for the different locations. So this is the third blade, and also we did for the similar parametric studies for the some different cases for the 18 and then multiple damages. So two damage, we use the damage in 2 blades and also in the 3 blades, and you can see all the cases which exactly indicates the damage locations. Once we find the damage, then we can numerically, and we go for the experiments. In that experiments, and if you see, this is the modal analysis kit, and this is the data acquisition system for the vibration, and this is the impulse hammer, and this is actually the accelerometers, and this is the magnet. Okay, this is the magnet, it's a very strong magnet, and this is a test rig that we have developed, and this test rig that we developed at the Swansea University, UK, and here this is the magnet which is kept at the root level of the beam, because if you see this, each blade is considered as a cantilever. It's a simple rectangular blade in cross section, and just kept the small magnet which alter the stiffness of the damage. And we use this hammer, we just hammer any blade, and then we apply the response on each blade, and then we use just shifted the accelerometer to other blade sets. Then we complete the entire blade for the 12 blades. Actually, for experimentally, we use to complete it for the 12 blades, and then we find that response of this. This is actually the tune. The blue color is indicates the tuned response of the blade, and the red color which indicates the mistuned blades. And there is some difference, significant changes. Unlike that numerical, we have seen that there are different behavior of the signal which mimics the entire that body of the blade. It's not only blade, which also disc and other associated components also, frequency also will be involved in this category. So it's very difficult to obtain this from the frequency response. There is a long, there is a large shift in the frequency. From here you can see the tuned one and mistuned, there is a large gap actually. So, and when you see this put in the well, when you apply this signal, this time signal into the well packet transform, and then you can see the spark pipe. That exactly we added the damage into blade number 2, and then we got that exactly that blade number 2 has this pipe, and which indicates exactly the damage location. So this is what we are applying the results from the static blade condition. So this is just a blade when it is in the static position, we just hammer it and then we can apply the response from the accelerometer and then we processed it. And we apply the response, time response, and that we convert into the frequency, time frequency signal, and then we use the Wheeler packet transform to find the energy damage index. And then next, after once you find out the location, the presence and the location of the damage, then the next task is to identify the severity of the damage. How much percentage of the damage that occurs in the blade. For that, we have used some mathematical index called the Lipschitz exponent. So this is actually used in the mathematics to identify the singularity that exists in the signal. So any singularity that happens due to some anonymous signal, so in the signal, so that can be identified by this fact, this term. Okay. So you can see the epsilon b. This is that is the you can say that is the abnormality term. So this is the constant which is the which varies with respect to the damage severity. So and this is the alpha, Lipschitz exponent alpha is always greater than 0 or point x equal to b. That means where that particularly signal that singularity that happens. Okay, so that means the damage happens. So this is a mathematical form, and finally we use this exponent, and for the different level of decomposition we obtained that, and then we found the alpha value. So that alpha which decreases with respect to the damage severity. And we have done the point of masses. That means instead of adding the damage, that means the damage we used by adding the mass. Generally we use this by reducing stiffness, but making or we can say that reducing stiffness by cutting the blade, that will be used for one time. So we cannot use it for the multiple purpose. Okay. So what we have done, actually we use that added mass, that means use magnets in terms of 11 grams each, and then we use from 11 to 98 grams. So and then we just keep on adding that so to increase the severity of the damage. And we have noticed that adding mass and then that increases decreases the natural frequency. Linearly, as we know that the damage reduces that means reduces the stiffness, right? When the stiffness reduction, then that means natural frequency decreases. So natural frequency decreases. Similarly, that adding a mass at that level also, it affects more than that the stiffness change. That means that contributes that for the damage. So the adding the mass also the decreasing which gives the effect of the natural frequency change. So that happens linearly over the magnitude of the mass. So it starts from the level to 99 grams. So this is what the trend we are obtained. And finally, we use this, and on top you can see added mass, and the bottom is see the stiffness reduction. So stiffness reduction, we just correlate this factor. That means 1% of signal, that the stiffness in numerical, that is equal to 10 gram of mass. So we just have computed this analogy that 1% of stiffness reduction, that is equal to 10 gram of adding mass. So you can see this is both, and under 99 grams, so which is equal to 9% of stiffness reduction in the numerical value. So the alpha value, which decreases exponentially, I can say that non-linearly, like here you can see this is the value which decreases, keep decreasing over when you are increasing that stiffness, when you decreasing the stiffness as well as that increasing the mass, okay. And that just gives an idea how this damage severity can be captured. So this is how you can capture the damage severity using the Lipschitz exponent. After that, so we have done the static blade test, then we have rotated the blades using, and then we captured the blade timings. Okay. So unlike this hammer test, so this is the actual experiments that we happen in the turbine blades. This is a simplified turbine model. Actually, we have fabricated this, and actually in a real turbine case, they use the active eddy current sensor and passive eddy current sensors and optical sensor. There are 3 types of sensors they use. And the optical sensor, the eddy current sensor is more rugged, and even if any oil or temperature, high temperature, you can use it. And optical sensor is very sensitive, and it's very sensitive to that heat and the temp and the other dust surface. Because when we use this kind of sensors in the real-time environment, because it is exposed to oil or gas, then the reliability of the sensor will come down. So the optical sensor will not be sometimes recommended for that situation. For this case, we have just tried with optical sensors, and all 3 sensors, how this in the performance of these sensors work for the damage mitigation purpose. Similarly, here is the piezo patch. We excited instead of using this hammer, instead of using the hammer, we use the piezo patch to excite the blade, and also here there is the magnet, that is the added mass, which replicates the damage effects. Okay. And this is how we have done that. We have taken the raw BTP, that means a blade tip timing signal, okay, from the active eddy current sensor. So this y-axis is the blade response in voltage, and then x is the time response. And for this 100 RPM, we go and we have computed for we have conducted the experiments for the 300 RPM. And after that, once I did that with this response, you see this is the identical peaks, like the periodic signals, and which and how we measure this response when the blade is passing this sensor, and this small amount of gap between the blade tip and the sensor. So the angular gap between the blade tip as well as the sensor edge end. So that is small amount of gap that forms. Okay, and so that will capture the blade passing. So that will give the blade passing time. This is generally called as a low sampling rate. So of course we passing in the signal, so it takes us a sample blade passing only. So it takes a peaks of that. When you remove when you see that identify the reference, we just remove one blade and just passing that one particularly in that particular removed blade, and we have the high response. That means high amplitude response that we get, that high response, or we can say high magnitude peak value that we get from the corresponding that location. That means it's called we just take the reference. Or any changes, because when you have a damage, that blade gets vibrates, and due to that is shifting, that time shifting happens. So due to that there is some lagging, the time lag. So that also indicates the damage. Okay, and sometimes the blade gets vibrates, then the blade extends, the blade lengthening happens. So the blade lengthening happens, so that may reduce the amplitude of the peak. So these changes also indicates the damage. So this way we can identify that the damage from the time domain, but sometimes very hard. So if you see this, it starts from blade 1 to the blade 2, blade 3, and this is the one entire cycle. Once it completes, then another cycle passes like that. So this is a periodic signal. So you can see this. And what happened when we have used this only one sensor results. I just taken one sensors and then I computed for both damaged and undamaged cases. And I had done some pre-processing, use some signal processing methods, and just convert that signal based on some pre-programming. After extracting the time signal, and then we convert this integer blade pulse. So I have done some signal processing work, pre-processing work, to convert this into the single blade response. Instead of taking all the blades, I will just consider the initial single blade for different 4 cycles, and here also this is for the tuned and this is the rectals and mistuned blades. And then the same signal we applied into the variable packet transformer, I did for the free variation problem. And the difference of these two, like you get this coefficient of this like this. So we also, it's very challenging for that when you just use this energy based mistuning index, and it's very challenging. And if you use this threshold and get a very small amount of value, just that spike, which indicates that exactly the damage location at the even the rotating condition. The blade number 8 I just used it, and got the spike that indicates the damage location at that even in the blade rotation phase. Similarly, I have done for the passive blade. So the passive blade is like there is a single spike there. So this is like only positive response you get from the active eddy current sensor. And if you see, this is the complete, like it starts from the negative and then it goes like this. So it's like one full cycle curve which compressed manner. So this is the kind of this is the signal of passive eddy current sensor. Okay. So this is also kind of taken for 4 cycles, and similarly for the tuned and mistuned, and applied to the variable packet transform, and then they use this variable packet threshold, upper limit. After applying this threshold, then you can see that exactly it gets the damage. And for the optical sensor here there is a like the active current sensor. This is a small. There is a small characteristic changes here. There's a small changes here. Here and this is not there here, and this is for the tuned blade. And when you see, this is the bump is there. The small bump happens because when the laser passes on the magnet, and the magnet because this is the damaged case. So that means the signal will use the bump. Okay, this changes in the characteristics due to the presence of the magnet. This is without the magnet, and when you pass this, and you get this signal like this. So what we observed that so all 3 sensors are even good, and for multiple cases we have done tried with different cases, but in the eddy current sensor, both passive and active eddy current sensor, and it doesn't work for the active only, the multiple damage, but whereas this optical eddy current sensor works very nicely for that, even for the multiple damage cases. And then next, then we quantify that using the damage. I said that, like earlier I said that exponent, we use it for this experimental also for the different damage cases, and it's start decreasing as we have seen for the static blade case, and it start from that like 11 gram to 99 gram. So it's keep reducing monotonically, and this curve so we indicate that the severity of the damage. So as the curve decreases, which indicates the increase of increasing the magnitude of the damage. So we can predict all presence, location, and the severity of the damage using the variable packet transform. In the summary, I just want to conclude that initially we modeled this the 2 degree of freedom lump parameter model. So employed to predict the fundamental dynamics of the data disk. So some papers have already done some work in the single degree of freedom, which used only the bare degree of freedom. So if you include the disk degree of freedom also, so which gives the complete dynamics of the data disk. and this paper was published in Academia, and this is the winner. And he introduced the Wheeler packet transform is a versatile method. I tried with different conditions for the low speed to high speed, and different damage conditions and severity conditions. All the cases, the Wheeler packet transform works well, and even we try for that, we are going to try for the even real case studies. And so what I want to say that there are many other techniques also available, like I said that previously, the Hilbert transforms, and there are different transforms are available. You can also try that. So this Wheeler packet transform handles only the non-stationary signals, but it doesn't handle the non-linear signals. Even if you use this the Hilbert transforms, that's the scope for the research in this field, that which work we can use it for the non-linear signals also. So it's very interesting, and you can keep working on it. But still, this method, that if you want to implement in this real-time environment, the results are more even noise environment. So that's very challenging task, and to extract the noise and then just denoising, and then we need to identify the damage. It's still challenging us in the scope for the research purpose. And these are the reference. So these are the two papers which comes out of this work, and one is published in the Acta Mechanica, and then there is a Journal of Shock and Vibration, and both are SCA journals. And thank you for patience and your listening. Questions?
Sir, thank you very much, sir, for your wonderful presentation on turbine blade vibration and condition monitoring. Really, it is a very grateful area, sir. Many of you don't know how to do the turbine blade condition monitoring, and your lecture will give you the wonderful idea about how the wavelet techniques and the blade tip timing, everything will be the new for us. Definitely it will be used for us to do our future research in this field, sir. Audience, please, if you have any question, please raise. Audience, please unmute yourself.
Yes, sir, I have a question, sir.
Yes, sir.
Yeah.
Sir, as you said, while adding mass, when you add mass, as I saw the graph, the natural frequency was decreasing when you increase the mass.
Yes,
sir. Sir, but
actually,
conventionally, when we add mass, the blade stiffens, no, sir?
Yeah, that is depending on the location of the blade adding, the mass adding. So let us say we have done this analysis. Let us say, as I said, that blade tip, any blade which is located in the disc, which is like a cantilever blade, right? So it's like nothing but like each blade is like a cantilever beam, okay, which is fixed to the disc. And if you see, when we add this one, okay, the blade, the mass which in the location, and what is the natural frequency form? So this effect actually, the natural frequency is the root of k by m, right?
Root of k by m, sir.
Yeah. So when the mass contribution is more than that, so in that case the mass is dominating this sometimes. Even the mass, adding the mass, what will happen? Reduces the frequency, right? While the denominator increases, what will happen? Obviously the natural frequency decreases, right? This is the logic.
Yes, sir, but I have confusion. Mass does affect the.
Some cases it's like when the mass adding, that will dominate the stiffness. Okay, the stiffness contribution will be lower at that time. Okay, but it's not the real. What our intention is that this gives an effect of like give the indication of the reduction, or you can say the changes in the blade characteristics. Okay. So the real case is like we can try the blade damage, like a socket or whatever. But physically, what happens? Practical conditions. If you make a blade crack, and we can since very costly things. If you even make a blade for one study, and you cannot use it for the many other other studies, right? So we have to use it for the other blade. So since it's a costly and actual method, like what we have said, like stiffness reduction, normally stiffness reduction is the thing, but this method gives an idea of for predicting the damage. So this is a kind of like hypothesis that we have brought actually. So this also bring the characteristics, change the characteristics of the response of the blade. So that we have seen in that the studies.
Yes, sir. Sir, why didn't you consider the gyroscopic effect into consideration, sir?
Yeah, that is a research scope. Yeah, that is also, see, in the numerical model, still we have done that. We have just considered that only 2D freedom without the centrifugal effects. That is stiffening effects. That's what I'm saying. We have still research for this scope for the research. We can consider the centrifugal stiffening, and then we can use this in the model 2D freedom. That's still a scope for the research. Due to the time constraints, we have done the numerical model. So that also pretty good. It shows a good response, which that means we got some good results. Here, if we have time, if we have more time, then we can do it. We can still try to do that one. Since the project time will be very limited, so we have to come up with some results. So we just come up with the 2 degree of freedom model. Yeah, there is a still, you can also try with that. You can trade the gyroscopic effects, and as I said, that the centrifugal stiffening as well as the rotating rotary inertia effects. So that is also a good contribution for the scientific community.
Sir, can I get your contacts, sir?
Sure. I will give it to Professor. Okay.
Thank you, sir.
Okay.
Sir, I have one more doubt, sir. Actually, you are adding mass in the turbine blades. Is there any possibility to delete the mass, sir, on the opposite direction for better balancing of that blade?
Yeah, actually, sir, our intention is to find out the changes in the response. That means altering the stiffness of the blade. We found that this is the simplest way of doing. So by adding this magnet, so we can easily change the magnet, change the mass of the magnet, and so we found there is a significant changes in the response. And but our objective is to detect that, or we can say that any changes in the stiffness. Okay, because the damage which causes the reduction in stiffness. But my work, like if you give any type of it may be a reduction or increase in the stiffness. So my algorithm will work. Okay, any changes in the stiffness, not only for the reduction, but also increase in the stiffness. Any changes in drastic changes, small amount of subtle changes in the signal, so that will capture my algorithm will capture that. Okay, any small changes, even that may be a positive side or the negative side. So in our study, damage generally causes due to the reduction stiffness, or you can say the reduction stiffness causes the damage. You can say that. So that reflects in the natural frequency.
Okay.
So when for a high, like a small amount of damage, it's very difficult for Fourier transform to capture. So that's what we have seen in that. I just explained it. It's very subtle changes. It's not because there are many problems while taking the measurements. Even for the sensor, like sensor error, or you can say the instrumentation error, or there are many errors, noise. So this all mask the natural frequency or changes in the that changes. Okay. Okay, so there will be some limited, at least 5% of natural frequencies change only. At least we can find out the damage for the in the fluid transfer in the natural frequency analysis. At least we need 5% changes. Unless otherwise, then there will be some experimental condition or due to the boundary condition or material property. There are several factors which affects the natural frequency. So, and that's what we use this time signal and directly take the time signal and convert the time frequency signal, and then we use the energy component. So this will mean even small amount of changes that will exactly shows that.
Sir, one more question. So what kind of error analysis required for validation of technique used in blade analysis? Sir?
Yes, sir. So actually, I have done. I have not shown anyway for the time constraint. I have done some error also. So I have taken some numerical analysis itself. I have considered the noise condition also. I have taken some Gaussian noise. Okay. So the random noise. Some generally say the Gaussian noise. So I just added some 10% up to 10%, okay, 20% noise we added to the signal, and then we still checked it what is the robustness of the algorithm. But in my paper, if you just go through, if you have time, then you can go through the paper in the published in Acta Mechanica. So that work actually, I just include the noise also. Then certain amount of noise, and then we still algorithm able to find out the damage, even the presence and the location of the damage.
Okay, sir. Thank you, sir.
Okay.
Any other question, audience, please? Participants? Okay, if no question means we will wind up this section. Sir, thank you, Professor Prakash sir, for giving this wonderful lecture for the budding teachers in this faculty development program. I thank you once again for you to spend your time in this busy schedule. Thank you very much, sir.
Thank you, sir. Thank you so much. It's for my, it's for me also. It's a pleasure to taking your invitation. And actually, my native is Erode only, so I'm always I'm more concerned about our regional place also. So I know. So I have already studied the Sangamani College. So it's my pleasure. It's my pleasure. Very good for you can have some collaboration also. In near future. Okay.
Sir, do share your contact, sir.
Sure. Okay, sir. I will contact. Maybe I will give it to sir, professor. You can just collect it with him. Okay.
We will send you, sir.
Okay, sir. I will give it to you, sir. Okay, sir. Okay, sir. Thank you. Thank you, sir. Thank you.
All participants plus the next session will start by 11:30. All of you be ready by 5 minutes in advance. The Dr. M. Amarnath from IIT DM Jabalpur will give a lecture on introduction to sensor and signal processing techniques for condition monitoring of rotating machinery. Meantime, you disperse and come back by 11:25 exactly. Thank you.